In this lecture on industrial robotics, we will be dealing with RoboCell design and control. In particular, we will be dealing with RoboCell layouts. Industrial robots generally work with other pieces of equipment. These pieces of equipment include conveyors, production machines, fixtures, and tools. The robot and the associated equipment form a workcell. The term workstation can also be used, but this term is generally limited to mean either one workcell with a single robot, 2. One work location along a production line consisting of several robo workstations. Sometimes human workers are included within the robo workcell to perform tasks that are not easily automated. These tasks might consist of inspection operations or operations that require judgment or a sense of touch that robots do not possess. Two of the problems in robo applications engineering are the physical design of the workcell and the design of the control system which will coordinate the activities among the various components of the cell. RoboCell layouts. Robo workcells can be organized into various arrangements or layouts. These layouts can be classified into three basic types. 1. Robo-centered cell, 2. Inline robo cell, and 3. Mobile robo cell. Robo-centered workcell. Figure 11.1 is the schematic of a typical robo-centered workcell layout. In the robo-centered cell, Figure 11.1, the robo is located at the approximate center of the cell and the equipment is arranged in a partial circle around it. The most elementary case is where one robo performs a single operation, either servicing a single production machine or performing a single production operation. Die casting, one of the very first applications for a robo, required the robo to unload the part from the die after each casting cycle and dip it into a quenching bath. Other production machine applications required the robo to both load and unload the work part. For some of these applications, the cycle times of the machine were relatively long compared to the part handling time of the robo. Metal machining operations are examples of this imbalance condition. This required the robo to be idle for a high proportion of the cycle, causing low utilization of the robo. To increase the robo utilization, the Workcell concept was developed in which one robo serviced several machines as pictured in figure 11.1. An application of the robo-centered cell in which the robo performs the process is arc welding. In this case, the robo accomplishes the production operation itself rather than servicing a production machine tool. With these robo-centered cell arrangements, a method for delivering the work parts into and or out of the cell must be provided. Conveyors, parts feeders with delivery chutes and pallets are the means for accomplishing this function. Machining, die casting, plastic molding and other similar production operations for discrete part production are examples of this case. These devices are used to present the parts to the robo in a known location and orientation for proper pickup. In arc welding, human operators are often used to accomplish the parts loading and unloading function for the robo. Inline robo cell. A typical schematic of the inline robo Workcell is shown in figure 11.2. With the inline cell arrangement pictured in figure 11.2, the robo is located along a moving conveyor or other handling system and performs a task on the product as it travels past on the conveyor. Many of the inline cell layouts involve more than a single robo placed along the moving line. An example of this cell type is found in car body assembly plants in the automobile industry. Robos are positioned along the assembly line to spot and weld the car body frames and panels. The three categories of transfer systems that can be used with the inline cell configuration are 1. Intermittent transfer, 2. Continuous transfer, 3. Non-synchronous transfer. One, intermittent transfer system. It moves the parts with a start and stop motion from one workstation along the line to the next. It is sometimes called a synchronous transfer system because all of the parts are moved simultaneously and then registered at their next respective stations. In a robo layout using intermittent transfer, the robo is in a stationary location and constitutes one position along the line at which a part or product stops for processing. The advantage possessed by the intermittent transfer system in robo applications is that the part can be registered in a fixed location and orientation with respect to the robo during the robo's work cycle. Two, continuous transfer system. This registration of the part relative to the robo becomes a problem when the continuous transfer system is used to move parts in the cell. With this type of transfer system, the work parts are moved continuously along the line at a constant speed. This means that the position and orientation of the part is continuously changing with respect to any fixed location along the line. The problem can be solved by using either of two means. A moving baseline tracking system. B, a stationary baseline tracking system. For details, refer the textbook. Three, non-synchronous transfer. The third type of transport system is non-synchronous transfer. It is also referred to by the name power and free system. In this materials handling system, each part moves independently along the conveyor in a stop and go fashion. When a particular workstation has completed its processing of a part, that part proceeds to move toward the next workstation in the line. Hence, at any given moment, some work parts are being processed while others are located between stations. The design and operation of this type of transfer system is more complicated than the other two because each part must be provided with its own independently operated moving cart. However, the problem of designing and controlling the robo system used in conjunction with the power and free method is less complicated than for the continuous transfer method. For the irregular timing of arrivals on the non-synchronous transfer system, sensors must be provided to indicate to the robo when to begin its work cycle. The more complex problems of registration between the robo and the part that must be solved in the continuously moving conveyor systems are not encountered on either the intermittent transfer or the non-synchronous transfer. Now let us move to mobile RoboCell. The third category of RoboCell design is one in which the robo is capable of moving to the various pieces of equipment within the cell. This is typically accomplished by mounting the robo on a mobile base which can be transported on a rail system. The rail system used in RoboCells are either tracks fastened to the floor of the plant or overhead rail systems. Figure 11.4 illustrates the concept of the track on floor system, while the overhead rail system is shown in figure 11.5. Figure 11.4 is a schematic of the track on floor mobile RoboCell. Figure 11.5 is a schematic of overhead rail system for a mobile RoboCell. The advantage of the overhead rail system compared to the floor-mounted track system is that less floor space is required. The disadvantage is the increased cost of constructing the overhead system. A mobile RoboCell would be appropriate when the robo is servicing several machine tools with long processing cycles. In this situation, the robo would be able to share its time among the machines without significant idle time for either itself or the machines it is servicing. The reference book used for this lecture is titled Industrial Robotics, Technology, Programming and Applications. The authors being Michael Gruver, Mitchell Weiss, Roger Nagel, Nicholas Audrey and Ashish Datta. This is the second edition of this book published by McGraw-Hill Publishers. The figures in this lecture were taken from this book. Thank you.